Thank you, Luciano, for the presentation. Good morning to everybody, ladies and gentlemen. And the work is based, is produced on natural fiber-based composite laminates. As you know, polymer composites are used in any industrial area, given to a lot of advantages with respect to conventional material. It is the lightness of the polymer composites, but also the corrosion resistance, the versatility, high strength to weight properties, in general, high specific properties. And among these, a lot of interest is dedicated to the fiber reinforced polymer composites because they are used in the many industrial fields as structural composites with respect to conventional ones that are based on metals or other metals. Polymer composites have some, in particular, thermoplastic composites have some advantages that goes from the toughness to the lightness to the recyclability. Intrinsic recyclability is important from an extreme point of view, but also the faster processing of these materials. But their wide diffusion is always has been limited and slowed by the high cost of tools and materials, but also by the strict know-how about design and manufacturing, but also by the low temperature for safe use with respect to thermosetting composite materials, because in this case we have a glass transition temperature that usually is lower than 100 degrees. In case of epoxy resins, you may have also or other thermosetting polymers composites. You may also have a glass transition that goes through 150 degrees or higher again, and this advantage has been enhanced in the last years by the advent of the so-called natural fiber composites. Because in this case, in particular green composites, because in this case we have a bio-based materials and natural fiber materials as reinforcement that usually have a lower resistance with respect to temperature, with respect to pressure that you may use to impregnate the fibers. And in this case, you have to take also into account that there is not uniform properties of the fibers. That depends by many situations, also by the humidity. And in this case, you don't have a good adhesion interface because you have a natural hydrophilic in a matrix that usually polymer matrix is hydrophobic, so interface is not very good, and all these challenges have to be faced. So starting with these two reasons in which the use of thermoplastic composites is limited, especially in such application, given the high viscosity of the molten matrices, because you have to impregnate with the polymer first, and you have to use high temperature to lower the viscosity, or to use high pressure. But in both cases, you may damage the reinforcing fabric or the reinforcing fibers. And take into account that this effect are enhanced in case of more sensible bio-based matrix and natural fibers. In that case, it's important to know that the need to have an increase of the knowledge of the materials, but also of the process in order to gain a good effect on the finished products. And so this work is produced on composites that are based on bio-based matrix, that is the polylactic acid, and Jute fibers that are organized in a fabric. There is a woven fibers. And the aim is to highlight which are the challenges from the technology point of view that you have to face in order to have a finished product with the properties that are competitive with composites based on synthetic raw materials. So we are made with the typical processing approach, that is the film stacking and hot compacting with the press. We combined the polylactic acid with the Jute fiber fabric, and we tested the specimen with the weighted sides that are cut directly from the plates that we obtained with this technique to obtain specimens for tensile tests and for flexural tests. And then we compare the experimental results with the theoretical results, and we see that there is a high discrepancies between these data. So these are the experimental results. The tensile tests and pressure tests, as I said before, we processed the stress strain curves in order to obtain some parameters, but I want to focus the attention on the modulus because we have determined this modulus also using a very simple theoretical approach, and we see that in this case, in case of tensile stress, in tensile proof, we have a Young modulus of 2.5 gigapascal that is very similar to the tensile modulus of the matrix, while the fibers have a highest elastic modulus, and the final product not approach this value. This is due to the fact that the fibers doesn't work at the best. As I said before, we determined the elastic model using a simple theory approach. We're using these two expressions to obtain the modulus during the weft along the warp, and we know that in case of our architecture of the texture, the decay is 0.5 because we have a plane wave texture in which the number of fiber along the warp is equal to the number of fiber along the weft. So we have the same rigidity in both directions. So we have to determine K is 0.5. We set this value 0.5 given the architecture of the fabric, and we have to determine the long-term Young's modulus by considering that which are the characteristics of the raw materials. In case of the isotropic matrix, from the technical database, we have 3.5 gigapascal, and about the fabric, we have 40 gigapascal of the fabric. So we have determined the refraction volume of the matrix and the fiber given the nominal area weight of the fiber, given the thickness of the fabric. Simply, it is possible to determine which is the amount of fiber inside of my plate, and we have determined as a consequence also the amount of the matrix. Given all these parameters and set this parameter inside of the simple model that I showed before, we may obtain which is the theoretical stiffness that we have to obtain in both directions, transverse and longitudinal direction, that is 10 gigapascal, if we take into account which are the characteristics of the matrix and the fibers. And we remember that the value, experimental value is lower, so there is a discrepancy, but this is expected, and this is enhanced, which is the challenge that we have to face. We have a matrix and we have fibers that have difficulty to stay together because interface is not good, and we have to compact by hydraulic pressure the matrix in order to have a good impregnation. This is difficult because when you heat the matrix, it's not a thermoset in which you have a liquid. Now we have a viscous fluid, and the viscous fluid, if you use a high temperature, you may degrade the matrix. If you use also the fibers, if you use a high pressure for compaction, you may distort, you may deviate, which is the right architecture of the texture, and you change all the kinetics of the impregnation. So we have to face this problem that you have during the development of this process. So the problem related by the percentage is that a new manufacturing process is needed, perhaps considering the physicalization of the matrix or the fibers in order to have a good quality interface, but also considering a good balance between the temperature and pressures in order to have materials that at the end, as finished the product, have properties that are comparable with conventional materials. Thank you very much.